I want to tell you that if weather permits, on Wednesday we will have a trip to Corcovado in the afternoon, and transportation will be free. We'll go from here to Corcovado, and in Corcovado you have to pay like $1,000, I think. No, like 13 reais, I think. But what you have to do is to go to room 208 and just give your name to know how many people will go and make arrangements for the buses. Okay? It's a trip to Corcovado. Corcovado, it's a big mountain where the Christ standing like this. He doesn't move. He's So, but please give your name, and if you don't want to go there, enjoy the city in some other way, because it's a very beautiful city that deserves your view. That is weather permits. If not, I still don't know what will be plan B, so that will be announced if weather doesn't permit. The buses will go from here directly after lunch. So, what? 2 o'clock. 2 o'clock. Last news. 2 o'clock in the afternoon. Okay.
This is Wednesday.
Yes, Wednesday.
Rui is going to talk again.
So it's a pleasure to introduce our next speaker, Professor Gabriel Paternain from University of Cambridge, who will talk on the stability condition in symplectic topology.
All right, well, thank you very much. It's a pleasure to be back here at this wonderful place, IMPA, and if there's a birthday party going on, that's even better. Yeah? So, feliz cumpleaños, Marcos. All right, so what I would like to talk about is a question that actually popped up as part of a project that I was doing with Kaichiri Bakanus Frauenfelder. The outline of the talk is sort of very simple. I will tell you first about the objects that I would like to discuss. I will give you a few definitions, taking into account that this audience might not be familiar with some of these, so I promise I will not rush. Then I will tell you about some of the technical tools that I would like to use in order to tackle the question that I will raise in the first part. In the third part, I'll tell you about the sort of main example, and I'll try to give some sort of idea of why this example answers the question that I will pose. All right, so I will begin with a closed odd-dimensional manifold. Yeah? And if I have a closed two-form, which is maximally non-degenerate, I will say that I have a Hamiltonian structure on my manifold sigma. Yeah? By maximally non-degenerate, I mean that if you look at the kernel of the two-form, it would be just one-dimensional. Yeah? So it has to have some kernel, because it's a two-form and a non-dimensional manifold, but I want that kernel to be as small as possible. Okay, so the kernel will be a one-dimensional space at every point, and therefore it's integrable. And the integral leaves, yeah, the one-dimensional curves that integrate that bundle are called the characteristic foliation of the structure sigma omega. Okay, and here is the main example that I'm sure many of you have actually seen at some point. So if you take any symplectic manifold and you take a function h from x into r, then any level set will give me such a Hamiltonian structure. Yeah? And as a matter of fact, the one-dimensional kernel of omega is actually spanned by. So if you look at the symplectic gradient of h, yeah, so this is the vector field that is associated with Hamiltonian H, that vector field will be in the kernel of this one-dimensional foliation. Yeah? So by doing that, we get tons of examples, and this is the main thing that one should have in mind. Okay, and as a sub-example, if you like, of this one, that might be actually more sort of familiar to this audience, is the following particular case. So if you take the tangent bundle of a manifold, or the cotangent bundle, whatever you like, if you like to work with velocities or with momenta, and you take a metric, you can always sort of pull back the standard symplectic form in T star m using the Riemannian metric, and you get another symplectic form in Tm. And then if you look at the usual kinetic energy, which is 1/2 norm of V square, well, that norm is given by the metric G, and you look at all those points and vectors with norm 1, that will give you a hypersurface, that I call Sm. These are vectors with norm 1, and in that case, this symplectic gradient is nothing but the vector field that generates the geodesic flow of your Riemannian metric. Okay, so this is the sort of objects that I have in mind, but of course the structures that I will have are certainly going to be a little bit more general than this, but I'll come back to the case of the geodesic flows at some point. Okay, now in the case of the geodesic flow, we have a sort of additional feature, and this is not, we certainly have this sort of two-form omega, but that two-form omega is very special. Yeah. So the two-form omega actually has a primitive alpha. Yeah. And that primitive alpha is what is called a contact form. It is a contact form because on the in the case of the geodesic flow, so for the case of the geodesic flow, if I look at the value of alpha on this symplectic gradient, I actually have the value 1 at every point. Yeah, so it's always different from 0. So you might have seen a sort of alternative definition of this is that if you look at the following volume form, this is actually, it is a volume form, in fact. Yeah? So here n is the dimension of the manifold. Okay, so in the case of the geodesic flow, the Hamiltonian structure is not just anything, but it's actually a contact one. Yeah? So it has a one form as a primitive with that sort of property. Okay, so now the concept of stable Hamiltonian structure tries to generalize the contact concept a little bit, yeah? So maybe I should just say, so here is one, I will tell you in a second why the name stable in this case. Yeah, as there are some words that has been, they are used for all kinds of things, and the word stable is one of them. You will see in a minute that in some reasonable sense it is stable, but in fact it's part of the point of the talk, that in another sense it's actually not stable. So it's a name that has been around for quite some time, and there's no point of changing it here. But so I will try to explain later on why the name. Okay, so what is a stable Hamiltonian structure? Well, you ask for a one-form lambda that has the property that if you take, if you like, any vector field in the kernel of this maximally non-degenerate two-form omega, it will annihilate d lambda. Yeah? And you want that form lambda to be non-zero on vectors on this one-dimensional subspace in the kernel of omega. Yeah? So let me a little bit of terminology. So if I have such a form lambda, then I have a nicely defined vector field, which I would like to call the rev vector field, and I will write these two equations here in case we need to refer to them, given by the property that lambda and r is equal to 1, and r annihilates d lambda, and of course this R belongs to the characteristic foliation, yeah? So I mean, the reason why you have that vector field is obvious, yeah? So there is one-dimensional direction, and if lambda is not 0 over that, then you just pick a vector field in which lambda is actually always equal to 1. Okay, and if you do that, then lambda will be obviously invariant under the flow of that vector field. You just use Cartan's magic equation to sort of check that. It's sort of immediate. And if d lambda happens to be omega, then we recover the concept of having a contact form, a contact Hamiltonians structure, yeah? Because if that lambda equals omega, then, well, this is saying exactly that this is contact. But the point about being stable is that the lambda and the omega are decoupled, yeah? They are only coupled in a very weak sense. The way in which they are coupled is just by demanding, well, the two conditions in the definition, yeah? So the contact case would be, if you like, sort of maximal coupling between the form lambda and the form omega. Okay. So I have given you an example of a Hamiltonian structure which is contact. Now let me show you that the stable concept is actually very natural, because there are plenty of examples of things which are stable but not contact. And here is one, a sort of very simple example. So basically, do the same thing. I mean, if you like, on this on the torus, just take the flat metric on the two torus, yeah. And rather than looking at the canonical symplectic form, just put a little twist on the symplectic form by adding the pullback of the area form on the base. So here the Q1 and Q2 are the coordinates on T2, and by pi I mean the sort of canonical projection from sigma onto T2, yeah? So here pi is the sort of obvious projection from this into T2, and I'm using here coordinates Q1, Q2 on the torus, and coordinate theta on the S1. So in this case, the unit circle value is just simply the two torus times a circle. And now the point is, well, we do get a very different sort of vector field. In fact, it's very easy in this case to sort of solve Hamilton's equations. You might want to think, if you like, as the system simply, maybe a system that you probably looked into high school physics. It's just the motion of a charged particle in the flat two torus, yeah? And the magnetic field is essentially given by that area form, yeah? So you put that little twist there. So that's a new symplectic form. And now you see there's no hope for this form to be actually contact, because it's not even exact, yeah? But it's very easy to check that it's actually stable, yeah? And in this case, the stabilizing one form, if you like, the form lambda, is kind of plain obvious. If you just look at the angular form, which is given by d theta, yeah, then it's very easy to check. I mean, it's a sort of exercise that if you find this vector field and you compute the angular form d lambda, and that vector field is always non-zero. Yeah? And since d lambda is actually closed, then it's trivially stable by the definition. So let me just again remind you about the definition so I don't have to go back in the slides. So stable, remember, I have this one form with this sort of two properties. The kernel of omega is contained in the kernel of the lambda, and then lambda is essentially non-zero on the kernel of omega. So in this example, you can see, if you like, maximal decoupling, right? Because it's the opposite extreme. The form lambda is actually very degenerate. Yeah. So it's really, this is, you know, the most faraway thing that you can think from a contact structure. Nevertheless, the concept of stability puts the two things, these two sort of examples, in the same bag. This is really the sort of one of the main merits, if you like. Okay. Right. Now I'd like you to sort of give you two other ways of looking at the stability condition. Yeah. So, okay. So one of them is actually this is sort of this I only realized after sort of talking with Chilibak for a little while, that this concept of stability in symplectic geometry, actually it was a sort of very natural thing back in the sort of 70s. And you know, this is what in the 70s Sullivan and Clark used to call geodesibility. Yeah? What is this? Well, you ask yourself the following basic question. You have a one-dimensional foliation, yeah, which doesn't have fixed points, and you ask yourself, can I find a Riemannian metric such that these one-dimensional foliations are the geodesic of that metric? A completely natural question, yeah? You would like to know that. So this was sort of quite a question that was looked at in some detail in the 70s. Okay. So, in fact, at that time, Sullivan was working on foliation cycles and gave a criteria for characterizing when a one-dimensional foliation is geodesical. Yeah? The criterion is actually quite nice, but in my view, kind of useless in a way. It's not really, I mean, you cannot really use it. I can tell you briefly what it says. So it says that a foliation is geodesical if you have a foliation cycle, that's basically some kind of invariant measure, which is arbitrarily if the following does not happen, which is arbitrarily well approximated by the boundary of a tangent to chain to the foliation. Okay, so you want to show that something is not geodesical, you have to go and find the boundary of this two chain and the invariant measure that is approximating. Well, good luck, yeah? Of course, you can give examples. I mean, the most obvious example is the case of a red foliation, in which it's kind of plain obvious. But except in those cases, it's actually very difficult to use it. I mean, it's sort of very nice, and it gives you a sort of feeling for what this condition is. But at the time of really sort of doing something with it, it's a bit frustrating. At least it has been for me. Okay, so that's another way of looking at that, and it's sort of very easy to see that these two things are the same if you think in terms of this one form and you look at the papers. It's actually quite straightforward. Okay, so that was sort of basically on the 70s, but then the sort of condition popped up with a completely different sort of definition in symplectic geometry. Yeah? So these were Hofer and Sender that essentially did not define the concept of Hill stable in this sense, but in the sense that I'm going to describe now. So they were really basically after proving the Weinstein conjecture and trying to sort of give examples of hypersurfaces of this kind for which you could show existence of closed orbits. Yeah? And they sort of developed very powerful methods for showing existence of closed orbits almost everywhere. Yeah? Not for the hypersurface that you wanted. Yeah, this always happens. Yeah, but for something nearby. But you want that one, not nearby. Yeah? So then they say, but if I have something stable, namely that I can foliate by similar hypersurfaces on which the characteristic foliations are conjugate, then I'm done, because if I find a closed orbit nearby, then I will have a closed orbit exactly on that one. Then they realized that the contact condition was giving you that, and then they say, but maybe this is something a bit more general, so why don't we call stable a hypersurface that has that property, namely that has a neighborhood with the property that every time that I look at a slice in that hypersurface in that neighborhood, the characteristic foliation there is conjugate to the one that I'm really interested in. Yeah? And they define it actually in that way, using the neighborhood and so on. And then it was actually much more recently, sort of about 4 or 5 years ago, that people realized that these two things that are on this slide are actually the same. Yeah? So what Hofer and Sender were looking at was exactly the same thing as the geodesibility in the 70s by Clark and Sullivan. Okay, so these are the two other ways you can think about this condition. Right, okay, so why do we care? Well, I just told you one reason why you could care, because if you're trying to show existence of closed orbits, but there is another reason, which was actually what prompted me to sort of look into that with Chilibak and Frauenfelder. And these are these flow homology type theories that one constructs in symplectic topology. So I'm not going to get into that, but I can tell you briefly what they all have in common. So all these things have in common. So basically you try to define some homology, you have a boundary operator, and this boundary operator is going to count basically holomorphic curves. Yeah? So in this case, you're going to have some holomorphic curve in a symplectization of this. So these things, I mean, I've been looking at the odd dimensional thing, but they can be sort of sit inside a symplectization, yeah? And there you have a sort of appropriate J, and there it makes perfect sense to talk about holomorphic curves, and then you would like to count them and look at the moduli space of that. And if you're going to count that, and you're going to look at the zero-dimensional component, and you want to count something finite, you need compactness. Okay? Now, it turns out, and this is the main thing, that the stability condition is the key condition that allows you to prove compactness of these moduli spaces. Yeah? So if you know that your hypersurface is stable, then you can show compactness, and you can start constructing some symplectic field theory. I mean, these things are actually ongoing projects. You know, these are not totally completed. And there is a sort of another one, which is Rabinovitz flow homology, which is useful for other sort of questions. Okay, so really this is the reason why you care about stable. Okay. Now, here is a sort of technical point. So, when you want to construct these flow homology theories, you cannot just do it on an arbitrary stable hypersurface. Your characteristic foliation has to be non-degenerate. What this means, so basically, I mean, in all these theories, you also count, besides holomorphic curves, you also look at the closed orbits of the characteristic foliation. And you want these closed orbits to be non-degenerate. So namely, that means that if you look at the sort of return map, yeah, and you linearize at the identity, you don't want one to be an eigenvalue, basically. Yeah? This is a sort of technical requirement of the theory. So, or you want something similar, something sort of more spot, in which the closed orbits, maybe they're not isolated, but they come in sort of nice families that you can actually control. Yeah? So you need one of those two conditions. Now, the way to sort of deal with that problem is the following. Well, I have a hypersurface, I can perturb the hypersurface a little bit, yeah? And then you think the closed orbits being non-degenerate is a generic condition, which it is, and then you run the theory there, and then you prove that it's invariant under small deformations, basically, yeah? Okay. Now, in the stable case, it is obvious that if you perturb, you remain stable, because, you know, just go back again to the definition. So stable just simply means that, contact means that I have a primitive of the symplectic form, and this primitive is positive on the vector field. So if I perturb, let's say, the form alpha to a new form omega nearby, yeah, since alpha is positive on the vector field, a perturbation will remain positive. Yeah? So the contact condition is open. So then things are fine. Yeah? If you start with an arbitrary hypersurface, you perturb a little bit, you make the orbits non-degenerate, then it's still contact, then you have compactness, and then the theory keeps building on. Yeah? So the questions that basically they have was, well, is this true in the stable case? Yeah? So if I begin with a stable hypersurface, is it true that if I make a small perturbation, which is exact, an exact small perturbation of this stable hypersurface, will I get something that is also stable? Yeah? So this was the question that basically popped up in these theories. Well, people hoped for quite a while that the answer was going to be yes, and the answer is in fact no. Yeah? So this is a bit of a drawback in these theories. So what I would like to do is to try to explain you why you have a negative answer. Yeah? So what sort of example shows that if we begin with a stable Hamiltonian structure, then it's possible to perturb it in order to get something that is non-stable. So in fact I will show something much more dramatic, that almost anything nearby will actually be not stable. So it fails in a sort of dramatic kind of way. Okay, so just before I tell you about the example, I need to tell you about some of the technical things that will go into the example. might be a good idea to sort of draw some pictures. So hyperbolicity is going to play a key role. So let me just, maybe some of you have seen this definition many times before, but maybe some of you haven't. So let me just sort of remind you a little bit. So one says that a flow is hyperbolic or is actually a nosov if one has a splitting. So namely, so imagine that I draw here these sort of flow lines. Yeah. So I have a flow line here, and I say that this is hyperbolic if you can split the tangent bundle into sort of basically three sub-bundles. One is the direction of the vector field, and then two more sub-bundles, which are usually called ES and EU, with the property that, you know, if you flow after time t, and you look at the same sort of picture, there will be here another sort of ES phi tx and EU phi tx, and they will have the property that if you look at a vector EU, then this in forward time will be expanded at an exponential rate. So basically this here is much bigger than that, and then on the stable the opposite will happen. It will be contracted at an exponential rate. Yeah? So this, at the linear level one deforms something like this into that. Yeah? Now if you have that uniformly, then you say that you have a hyperbolic flow. Okay, I will give you examples in a second. I'm sure you know many of these examples, but okay. Now, hyperbolicity is invariant under time changes, so this is very easy to check. So this was defined for a flow. Remember that I'm talking about a foliation, but you know, if it is hyperbolic for one vector field, it will be also hyperbolic for any time change of the vector field. That's easy to see. So this is, the hyperbolicity is an intrinsic property of the characteristic foliation. Okay, now the other thing that it's important for us to point out is that actually the weak bundles, one usually calls the weak bundles the sum of this EU plus the flow direction and ES plus the flow direction, those will actually also be sort of intrinsic to the foliation. They will not change if I perform time changes on my vector field. That's also easy to see. The other ones will change drastically, this ES and EU. But the sum of the two, the sum of the stable with flow direction will actually remain unchanged. So namely, if you do a time change, by a time change I mean I run the flow with sort of different velocities. I would just simply be moving the EU inside EU plus RF. Yeah? Okay, now here comes the key sort of technical point. Okay, so I'm going to say that this Hamiltonian structure is half pinch if I have a balance between the two constants that I had in the definition before. So namely, there was that sort of constant A and the other constant little a. So I will say that it's half pinched if the big A is strictly less than twice the little a. Okay? You'll see in a minute why this is important. Okay, but the first example that I want you to think about something being half pinched is take the geodesic flow of a hyperbolic manifold, a manifold with constant negative curvature -1. Yeah? So in that case, and I'll come back to that in a minute when I talk about the example, but in that case I can sort of tell you briefly is to sort of convince you quickly about this. You solve, you've done that in the many times, I'm sure, even while lecturing your courses in Riemannian geometry, you solve the Jacobi equation, yeah, and the solutions are, you know, e to the t, e to the minus t, basically, and this is sort of uniform, yeah. So all the sort of exponents are basically the same. So in that case, the two a's are actually the same and equal to -1. So it's not just half pinch; it's kind of super pinched, if you like. It's the best possible pinching. Yeah. Okay. Now the other thing why the half pinching condition is going to be great for us is because in that case is a standard result in hyperbolic theory that if you have something half pinched, then the weak bundles will be C1. So maybe I'll just register this here. So these two guys will be of class C1. So in principle, if you have a hyperbolic structure, there is no reason to expect any sort of regularity on these two bundles. Yeah? In general, you know that they're just continuous or wholly continuous. But if you have this sort of pinching, between these rates of contraction, then it's a standard result. This is to Pugh and Shoup that says that these two bundles are actually of class C1. I will use this C1 in a crucial way in a minute. Okay, now if I have the 1/2 pinching condition and stability, then I'm going to be able to introduce a connection that is actually sort of tailor-made for these kind of problems. This is called the canal connection. I will explain it to you in a minute. But this canal connection was a very useful tool, let's say in the sort of late 90s when discussing rigidity questions for geodesic flows and manifolds with negative curvature. Yeah? Okay, so what is this canal connection and why we can define it when we have something stable? Well, suppose you have now a stable hyperbolic Hamiltonian structure satisfying the 1/2 pinching condition, like the case of a geodesic flow in a hyperbolic manifold. Okay? Right. Now, for the Reb flow, so remember the Reb flow was this special parameterization of my characteristic foliation, for which this stabilizing one form is 1, and this is equal to 0. It's very easy to check that the sum of the stable plus unstable actually gives exactly the kernel of this one form. Yeah? The reason for that is easy to explain. So since this lambda is actually invariant, yeah, if you stand on a vector which is, let's say, stable vector, and you look at lambda on that vector, since you have invariance, as you move forward, this will be shrunk. Yeah? But lambda is invariant, so you let t go to infinity, and then lambda will have to vanish on every stable vector. Similarly, it will have to vanish on every unstable vector, so therefore the kernel of lambda has to be that. Yeah? Standard argument. Okay, now why is this good? Well, because I know that the weak bundles are actually of class C1. So for the vector field, for the red vector field, and only for the red vector field, which is, so only for the flow traveling with that particular speed, these strong bundles will also be of class C1 because they are the intersection of these guys which are of class C1 with a C-infinity hyperplane bundle. Yeah? So if I have something stable combined with the fact that these two guys are C1, it produces these two guys, ES and EU, to be C1 for the particular parameterization given by the red vector field. So then I'd like you to sort of think about this picture now, but this now for R, if you like. Yeah? Now these two bundles are of class C1 now, and using these two bundles of class C1, I can define a connection as follows. So you introduce first a pseudo-Riemannian metric, and then I'm going to take a connection that comes from that pseudo-Riemannian metric. Yeah? So I look at the following non-degenerate bilinear form, which takes a sort of bit of time to digest. So in fact, well, if you look at that, it's not that difficult. Everything being claimed here is completely trivial to check. I mean, the fact that this is symmetric and non-degenerate. But maybe the way one should sort of think about that is that once I tell you how this canal connection is defined, it's really the properties of a canal connection that are going to be relevant rather than really the way it is defined. Yeah. Anyway, you look at that pseudo-Riemannian metric, and now the connection comes as, you play the same game as in Riemannian geometry. If you have a pseudo-Riemannian metric, there is a unique connection which is compatible with the metric and has a prescribed torsion, yeah? Okay, now this connection is just going to be Z0, but that's enough, yeah? Because, so why is this Z0 only? Maybe I should go back. This pseudo-Riemannian metric is only of class C1 because I'm using here very heavily the splitting of the tangent bundle in the stable and unstable. Yeah, so I know that these two guys are C1, so therefore the Riemannian metric, the pseudo-Riemannian metric is C1. So therefore, the connection I can only claim to be Z0, of class Z0. But there's a unique connection of class Z0, which is compatible with this pseudo-Riemannian product, and it has that torsion. Okay, so probably the question you have in your mind is, I mean, why do you take that torsion, not torsion field like everyone does? Yeah? Well, the question is that if you want the connection to have certain properties, you need precisely that torsion, yeah, once you do the calculations. Okay, so what are the properties that this connection has, which are very nice? Well, it has the property of being invariant under the flow, yeah, and the connection actually preserves the splitting here. So namely, if you take sections of this bundle, the connection will map these things to themselves. Yeah? So these are the reasons for having those two properties. Okay. Right. How is the connection going to come for us? Why is it going to be useful for us? Well, the key lemma is the lemma that I stated there, so I like to sort of give a proof of that. Or tell you at least what is making this thing tick, yeah? So why is that d lambda parallel, yeah? Well, so this is a 3 tensor, yeah? So it's going to have basically 3 entries, let's say, yeah? Okay, now, lambda is invariant under my flow, d lambda is also invariant under my flow, and the connection is invariant under the flow. Therefore, this whole tensor is invariant. Okay? So therefore, this thing will be the same thing as flowing right? Okay. Now, suppose I have different possible choices for those psi I, but this will illustrate quite clearly, I hope. So suppose, for example, that I take 2 of them on the stable bundle, but the other one on the unstable one. Yeah? So in that case, I can make this in absolute value less than, well, there's going to be some, I call all the constant C, yeah? It's not going to be the same as the other C. There's going to be some constant, this is all continuous, yeah? There's going to be some constant times this. Now, times the norm of that. Now, this guy is shrinking stable vectors by a factor of e to the minus little at. Now, this guy is doing the same because they're both in the stable direction. Unfortunately, this guy is not doing that. This guy is actually expanding, but he's expanding with a rate given by e to the big AT. Now, the 2 little a's win over the big A. That's the half pinching. Yeah? That's half pinching. So, when you have that, that goes to 0. Yeah? So that you can do with all possible combinations of stable and unstable vectors going forward, backward in time, and you end up showing that this is actually 0. That's the proof of the lemma. Yeah? This is the half pinching. Okay. Great. So, the example. The example is the geodesic flow on a hyperbolic manifold, 3 manifold. Yeah? So my sigma is going to be the unit tangent bundle of the geodesic flow of a hyperbolic manifold. Yeah? It's a 5-dimensional example. Yeah? Okay. So, okay, but there's a twist. Okay. So I already mentioned that the geodesic flow has the contact form alpha. But in the hyperbolic case, and only in dimension 3, there is someone else. Yeah? So this is perhaps something that is, maybe, I don't know if you have seen, but I mean, there's a kind of remarkable thing going on here with the geodesic flow of a hyperbolic 3 manifold. And if you look at the space of invariant 2 forms, yeah, look at the space of invariant 2 forms, it's actually 2-dimensional. The space of invariant 2 forms is actually 2-dimensional. There is obviously d alpha, which is invariant. This is actually Hamiltonian, but there is some other form. Yeah, there is some other form psi that I would like to describe to you. Now, why I'm saying this is remarkable, because this only happens with the geodesic flow of hyperbolic 3 manifold. If you look at all the other hyperbolic manifolds, the only case in which the space of invariant 2 forms is 2-dimensional is in dimension 3. Yeah? And there is a sort of obvious reasons I will try to explain in a second. So what is that other additional form psi, which is going to be important for us? Well, let me tell you about it. It's quite nice if you haven't seen it before. So So where does it come from? Okay. So now you have to think in this example that these guys ES and EU, these are two-dimensional. And maybe even for the rest of the talk, think about these guys as being two-dimensional. Okay, so where does this form come from? Well, take a vector V in H, so this is, you take a point X in H3, I take a vector with unit length, and look at the plane that makes a right angle with V. Well, here you can rotate by 90 degrees. You can rotate by 90 degrees. So if you have a vector, you can multiply it by that, simply by the orientation of the surface, yeah, making this into an orthonormal basis. Okay, so with that complex structure, but it's a complex structure that depends on V, yeah, it's only on the tangent to V. It's not a complex structure on H3, but rather on the unit sphere bundle of H3. It's not even going to be there, but it's going to be in the right place, yeah. Okay. So how can I define this? So I'm on my way to sort of defining this sort of additional two-form psi. Okay, so let me remind you that a tangent vector to the unit circle bundle of H, to the unit sphere bundle of H3 can actually be sort of identified into horizontal and vertical components, yeah? This is kind of simple. If you have something tangent to the tangent, the horizontal component you just simply project, and the vertical component is the connection. Okay? Right, so I call those psi H and psi V. It's a usual identification with vertical and horizontal components. Okay, and I'm going to define a JV, which is a map from the tangent space to V to SH3 by itself by that formula. Yeah? So it flips psi V with psi H, but at the same time, it makes them rotate by pi over 2, sort of according to that map. Yeah? But this changes with V. It changes V. Okay. Right, so there is your two-form. So basically, you now couple this J with psi. With d alpha. Yeah? So I define now psi of psi eta as d alpha of J psi eta, and you can write it very explicitly. Okay, so you might say, why is this invariant to begin with? Yeah, I said this was a space of invariant two forms. Well, maybe I'll show you in a minute why it is invariant, but it's actually quite easy. So, well, first, I mean, I've done this in H3, but this clearly descends to any compact quotient, yeah? The whole thing is invariant under isometries. Okay, this was what I was telling you before. So in order to check that the form psi is actually invariant, you need to solve the Jacobi equations, because you want to know, I mean, in this case, you can find fully what the differential of the geodesic flow is. It's very simple. So I've written there for you. So you solve these Jacobi equations, and in this case, you find the stable and unstable bundles quite easily. In fact, maybe even so the way you sort of think. The picture is basically something like this. So if you're looking, so the geodesic vector field comes out of the blackboard, yeah, so you're going to have here a vertical subspace, a horizontal subspace. This will give you the identifications psi h, psi v, and the stable and unstable bundles sit like this, quite nicely, in the diagonal and the anti-diagonal. Yeah, that's completely elementary, and in fact you can actually find exactly what the geodesic flow does to each one of those guys. So it expands by e to the minus t, and it expands by e to the t. Yeah. Okay, and now it's immediate to check now that with these formulas that d phi actually commutes with j. Yeah, because this little guy IV behaves very well with respect to parallel transport. Yeah, so it's almost immediate. It's yeah, there's very little to do. So since it commutes with j, and this is the key feature of this geodesic flow in a hyperbolic manifold, there is. So also the J maps stable bundles to itself and unstable bundles to itself. So basically this is a geodesic flow that has an invariant conformal structure in the stable and unstable bundles. Yeah? And this additional invariant to form comes from that, and this only happens in dimension 2, basically. Yeah? I mean, there is an analog of this for higher dimensional hyperbolic flows, but then in that case, you don't look at the space of invariant 2 forms, but you look at high dimensional invariant forms. Yeah? But not for 2 forms. Okay, and the lemma is that the claim is that SM is actually a Hamiltonian structure, not with respect to the alpha, but with respect to this other psi. Yeah, so I have two. The space of invariant 2 forms is two-dimensional. And I'm going to look at the Hamiltonian structure that comes not from the alpha, but from this additional invariant 2 form. Yeah? And for that you need a lemma. Well, you need a lemma saying first that you want psi to be closed. Yeah? In fact, we'll show that it's actually closed, but not exact. Yeah? And then it has some additional features, is that the psi square is actually exact. And it's stable because it's being stabilized by the form alpha. Yeah? So the form alpha, I mean, this was already contact with respect to something else. So that form alpha now is my new lambda. But these two things are not, I mean, they are not related by, yeah? So they are kind of independent. They are actually the generators of these spaces of invariant 2 forms. Okay. Now, how do you see this property that, for example, the psi is closed? Well, it's actually, after I've done this argument, there's really nothing to do. We can just sit back and relax and look and say, well, psi is invariant, deep psi is invariant. This geodesic flow is certainly, super half-pinched. So this very same argument will show that deep psi is actually equal to 0. Yeah? So then the form is actually closed. Okay, to check that it's non-degenerate, is just from the definition. And I claim there that the form psi was actually not exact. Yeah? Okay, so here's a way to see that it's not exact. So there's a very simple geometrical reason why it's not exact. And this is because it integrates to non-zero on tangent spheres. Yeah? And these tangent spheres have, give a homology class which is non-zero at the level of SM. Yeah? Okay, and the reason why that integral is non-zero is, again, a very easy calculation. Every vertical vector has the form 0 omega or 0 u. You just go back to the formula and you see that this is essentially giving you the area form of the sphere. So it integrates to something that is non-zero. Okay. All right, and then there was a sort of additional claim that psi square was actually exact. Again, it's very easy to see that using transitivity of the geodesic flow, because, I mean, if you couple that, again, sort of simple argument, you look at these two forms, this and this one. So these are two top-dimensional forms. Yeah? So two top-dimensional forms are related by a function, but they're both invariant. So this function is also invariant. It is transitive. The function is constant. So if the function is constant, one is a constant times the other. And now you just simply contract with the geodesic vector field. Those give you 1. The geodesic vector field kills those two. So you end up having with psi square a constant times the alpha square. So therefore psi square is exact. Okay, so this is the example, and this is the claim. The claim now is that a typical Hamiltonian structure near this one, yeah, is not stable. Yeah, and when I say typical, I say that nearby, there is a sort of open dense set. So if you like, there's a sort of open and dense set of exact perturbations of omega for which it will not be stable. Why? So let me tell you what is the driving idea here. So what have we seen with this example? So we've seen with this example that the space of invariant 2 forms is two-dimensional. Okay? Now I'm making a perturbation of psi, which has a non-zero cohomology class. Okay? So therefore the new Hamiltonian structure will also have a non-zero cohomology class. if it were to be stable, there will be this other form, d lambda. Yeah? So then the space of invariant two forms will also have to be at least two-dimensional, because these two things cannot be one a multiple of the other, because one is exact and the other is not. Okay? Right. So the space of invariant two forms is two-dimensional. Now, the main idea of the theorem is to try to show that that two-dimensionality imposes the presence, you have to show, the sort of existence of a complex structure in the stable and unstable bundles that commutes with the geodesic flow, with the perturbation, with the flow of the perturbation. Once you have that, then you're in business, because having an almost complex structure is a highly degenerate thing. Namely, you just focus on a closed orbit, and it's very easy to make a perturbation of that to destroy the conformality on the stable and unstable manifolds. Yeah? So basically now the argument is, okay, well now we have to perturb, and I have to produce some argument that gives me this almost complex structure on the stable and unstable bundle. Once you have that, then it's a sort of fairly easy standard local perturbation argument to show that that can be easily destroyed. Yeah? So therefore, nearby things cannot be stable. Okay. Now, how do I get this? So now that all the work improving the theorem is trying to show that nearby things will really look like, if they were to be stable, like the geodesic flow case. Yeah? Okay, and this is just the last two slides, so I'll tell you briefly. I think I just say a few more words about the outline that I've just given you, but that's basically it. But I'd like to just simply tell you where the various things come in. So we make a perturbation, so we take an omega near psi with the same cohomology class. Then I know, I just said that we'll have a non-zero cohomology class, but the square will be exact. So the geodesic flow is half-pinch, but it was a lot more than half-pinch. There was a lot of rooms in the constant. So nearby things will remain half-pinched. Yeah? So therefore, if nearby things remain half-pinch, I can run the whole thing. Namely, I will have C1 stable and unstable bundles. I will have the canal connection. So I will have all the tools, yeah? Because the geodesic flow at the hyperbolic manifold has enough room to make this perturbation. Yeah? So that's the second point. So if it is stable, then you can write d lambda as, this is just linear algebra, as some bundle map L, yeah, in that form. Now, since I know that d lambda is parallel with respect to lambda, that was the key lemma, then L is also parallel. This would be a sort of important thing. So now basically what you do is you can show first that L splits into stable and unstable parts. So you can just do the argument on one of the bundles. Yeah? And then you say, well, I know nothing about the eigenvalues except that they have to be constant, because the whole thing is transitive. Everything is invariant, and the characteristic polynomial will have to remain constant. So suppose I have a complex eigenvalue. The claim is that, in fact, if I define J by that will be a parallel almost complex structure for the geodesic flow. And this is sort of the heart of the argument. Basically, what you have to do here is to say, well, this sort of requires that first the eigenvalue has a non-zero imaginary part. If it had a zero imaginary part, then you would be essentially producing a non-trivial subbundle of the stable bundle. Yeah? But a non-trivial subbundle of the stable bundle, if L is parallel, will remain of constant dimension. And since these bundles are actually transversals to the two spheres, you will be producing this one-dimensional thing inside here, will be producing a one-dimensional subbundle of the two sphere, which doesn't have. Yeah? So there are arguments of this kind that you have to put in together. Yeah? So that's basically the main point, if you like. And then this is exactly what I said before. Once you know that you have this J that is invariant under the Hamiltonian, under the flow phi t, then is a local perturbation argument to show that you can actually destroy this, if you like, sort of conformal behavior on the stable and unstable bundles. Okay. Thank you.
This one half pinching condition, is that implied by one polar section curve division?
By strictly quarter. Yes, exactly. But it's not for the complex hyperbolic space. So the complex hyperbolic space fails exactly. Yeah. So it has a 2-1 resonance. But if you're just a little less, then yes. Then you have. Sorry.
Any other examples besides four-pinch hypothesis?
For which you have half-pinched? In the geodesic flow case, not that I know of, actually. Probably you can construct, but I mean the standard thing to produce examples is to sort of assume the strict quarter pinching, which in this case, is.
Salvo 3 is pinched as you say, but it's not mathematical.
So, but that's not hyperbolic, yeah?
You said another example.
But I mean the half pinching condition that I've given is only in the case in which you have a hyperbolic flow.
Not anisole.
Anosov is the same thing, but in the soil it's not anosov, yeah? The geodesic flow is not. No, it's not. No.
No, not the geodesic flow, but you have an anisole flow.
Oh yeah. Well, that's. I mean, but that's okay. Yeah. I mean, certainly. So the answer is yes. You can produce lots of other algebraic examples, but I thought you were asking about geodesic flows, which were half pinched but not had curvature between 1 and 1/4. Is that what you were asking? Yeah. Okay. So yes to both, I guess. I mean,